And as models grew larger, another conflict emerged: the scarcity of labeled data. Language models could learn powerful representations from predicting the next word, but downstream tasks like sentiment classification required labels, true categories assigned by humans. Creating labeled datasets is expensive, time consuming, and often requires domain expertise. You might need experts to annotate medical reports, lawyers to annotate legal text, linguists to annotate syntactic structures. Without large annotated datasets, training a powerful model for each task from scratch became impractical. Even if transformers were capable of learning deep contextual representations, how could practitioners train such models without the expensive labeled data required for supervised tasks? This problem became more pressing as NLP tasks diversified. Some tasks involved classifying a single sentence, others required comparing two sentences to determine paraphrase relationships. Yet others demanded labeling each token in a sentence, such as part of speech tagging or named entity recognition. Each task required slightly different output structures. The field lacked a unified approach for handling them. Should one design a new architecture for every task? Could one reuse the same transformer encoded but modify the classifier? How would special tokens be handled? How could a model trained for predicting masked words be adapted for tasks that required sentence level or token level predictions? Even the fundamentals of sequence handling became a point of friction. How should the model interpret the entire sentence sequence when making a decision? Should it use the final hidden state? Should it average all token embeddings? Should it add special tokens to mark boundaries? The lack of standardization complicated research and engineering. Without a unified system, the advantages of transformers could not be fully leveraged. Thus, the conflict escalated. Static embeddings could not adapt. RNNs were too slow and forgetful. Transformers were powerful but difficult to train from scratch. The abundance of unlabeled text contrasted sharply with the scarcity of labeled data. The field needed an innovation that unified architectures, connected pre training with downstream tasks, and provided a clear mechanism for adapting a large language model to many different problems without requiring massive annotated datasets for each. The solution would require combining transformer strength with a new perspective on how models acquire linguistic knowledge. A set of tensions created the perfect conditions for the next revolution: a system that could absorb massive amounts of text, learn contextual representations of language, adapt itself to the new tasks with minimal labeled data, and provide a single architecture capable of handling classification, sequence labeling, sentence pair modeling, and more. And that system was birthed, and its introduction marked the turning point that resolved nearly all the conflicts that had accumulated across decades of NLP research. The conflict that had been building for years in the field of natural language processing finally reached its breaking point when the transformers arrived. The earlier approaches of static embedding, sequential recurrent neural networks, and limited context window had each brought the field forward and then revealed severe structural weaknesses. Word2vec could not contextualize ambiguous words, RNNs could not parallelize and struggled to carry information across long range sequences. Even bidirectional RNNs, though more expressive, remained fundamentally constrained by recurrence and gradient instability. The need for a model that could look at words at once, incorporate both left and right context symmetrically, resolve ambiguity dynamically, and leverage massive unlabeled corpora had become undeniable. The transform architecture stepped forward at precisely the moment when the field was ready to leap into new paradigm. Transformers introduced new challenges, namely quadratic computational cost and sequence length, and the need for fixed input sizes, but they unlocked a profound new capability: deeply contextualized bidirectional understanding of sentences. This paved the way for the next leap, using transformers to learn general language representation from massive corpora and then adapting these representations to downstream tasks through fine-tuning. The transformer introduced in the paper, "Attention is All You Need," broke decisively from the idea that sequence models must operate sequentially. By replacing recurrence with self-attention, transformers made it possible for each word to directly attend to every other word in the sentence, regardless of position, direction, or distance. In practical terms, this meant that when the model encountered the word bank, it could immediately look not only at the words that came before, but also at those that came afterwards, like river or account, and use them to infer the correct meaning. Instead of being forced to process sequences token by token, transformers enabled models to process entire sentences in parallel. This architectural shift unlocked a level of contextual understanding that RNNs could not match. To understand how transformers achieve this, we must look closely at self-attention mechanism. Each input token begins with non-contextual embedding, typically obtained from an embedding table similar to word-to-vec, but randomly initialized at the start of training. For each token, the model computes three different vectors by applying learned linear transformations: a query vector, a key vector, and a value vector. The query represents what kind of information this token is seeking. The key represents the kind of information the token offers. The value represents the content that may be passed along if attention is assigned. Self attention then computes the similarity between the query of one token and the key of every other token using a dot product. This produces a set of attention scores, real numbers that indicate how relevant each token is to token being updated. The model then normalizes these scores via a softmax function so that they form a probability distribution. These probabilities weight the value vectors of each token, and then the final target token is the weighted sum of all value vectors. This entire mechanism is differentiable so that the model learns during training which tokens should attend to which and how strongly. Transformers do not rely on single set of queries, keys, and values. Instead, they use multiple attention heads, parallel sets of QKV matrices, each of which can learn to focus on a different type of linguistic relationship. One attention head might specialize in learning syntactic dependency structures, another in capturing subject verb agreement, another in resolving co-references, and yet another in recognizing semantic roles. Although we cannot force a head to specialize in a particular pattern, experiments and visualization techniques reveal that these specializations emerge naturally during training. The outputs of all heads are concatenated and passed through a feed-forward network that further transforms the representation. Each transformer layer contains this multi-head attention block, followed by a feed-forward block with residual connections and layer normalization applied after each sublayer. Stacking these layers, often 12 or 24 or more, produces deeply contextualized embeddings that encode rich linguistic information. Because transformers do not rely on recurrence, they require positional encoding so that the model knows the order of tokens. These encodings are either sinusoidal or learned and are added to the input embeddings at the bottom of the transformer stack. With the position information incorporated and fully bidirectional attention available, the model can interpret sentences with far greater flexibility than RNNs. It can attend to any word in the sequence regardless of the distance, thereby eliminating vanishing gradient problem that plagued architectures like RNNs. Moreover, because all tokens can be processed in parallel, transformers can leverage modern hardware efficiently, accelerating training enormously. Yet the full power of transformers would not be realized until the next great idea: pre-training followed by fine-tuning. The insight behind pre-training is that massive amounts of unlabeled text, blogs, news articles, encyclopedias, books contain deep patterns about language that a model can learn simply by trying to predict masked or missing words. Training a transformer from scratch on such text allows it to learn representations that capture grammar, syntax, semantics, even aspects of world knowledge. Once this general linguistic competence is acquired, the model can be fine-tuned with relatively small labeled datasets to perform specific tasks such as sentiment analysis, question answering, named entity recognition, paraphrase classification, or token level tagging. Bidirectional encoder representation from transformers. BERT's training objective combines masked language modeling with next sentence prediction. In masked language modeling, the model randomly replaces some input tokens with a special mask token and trains itself to predict the original token based on the surrounding context. This forces the model to learn bidirectional dependencies. In the next sequence prediction, the model receives pairs of sentences and has to determine the second sentence naturally follows the first in the original text. This trains the model to understand relationships between sentences, which is crucial for tasks such as question answering and lateral language inference. Once BERT is pre-trained on large corpora such as Wikipedia or book corpus, it becomes extremely powerful to fine-tune. To perform sentiment classification, one simply adds a dense classifier on top of the final embedding corresponding to a special token that BERT inserts at the beginning of every input. Because all embeddings after the final layer are fully contextualized, the embedding for CLS serves as a holistic representation of the entire sequence. Feeding it to a classifier produces a sentiment label. Fine-tuning is performed end-to-end, but with smaller learning rates so that the pre-trained parameters are adjusted gently to fit the label data. For tasks involving pairs of sentences such as paraphrase detection or lateral language inference, BERT concatenates the two input sequences with a SEP token in between, then uses the CLS embedding to perform classification. For token level tasks, like part of speech tagging or named entity recognition, BERT processes the entire input through the transformer layers, and the final embedding for each token is fed individually into a classifier. This allows the model to label each token in a contextually informed manner. Because BERT's architecture is flexible and standardized, it can be applied consistently across tasks. Implementing BERT in frameworks like TensorFlow Hub or PyTorch is straightforward. One loads the pre-trained model as a Keras layer, for example, along with its input placeholders for word IDs, masks, and segment IDs. BERT outputs both the CLS embedding and the sequence of contextual embeddings for each token. The practitioner attaches the appropriate classifier for the task, compiles the model, and fine-tunes it using labeled data. BERT's success stemmed not only from its performance but also from its practical accessibility. The introduction of BERT triggered a wave of follow-up models. Roberta revisited the pre-training process, removing next sentence prediction and training longer on larger batches, yielding improved performance. Albert introduced parameter sharing across layers and factorized embeddings to reduce the model's memory footprint. Mobile BERT and Tiny BERT were optimized for resource-constrained environments, enabling faster inference on edge devices. These models built on Transformer Foundation while refining aspects of the training objectives, architecture, and the parameter efficiency. Then came the Transformer, and with it, a new set of complexities. While the self-attention mechanism solved many of RNN's limitations, Transformers introduced heavy computational requirements. Self-attention has a computational complexity of O of n squared times d with respect to sequence length. Because every token attends to every other token for the sequences of length 512, this means over 250,000 pairwise interactions per layer. For sequences of length 1024, the number quadruples. When you multiply this to dozens of transformer layers, training requires significant compute power. Transformers also require fixed input lengths. They cannot naively handle sequences of arbitrary size. Instead, they impose maximum token limit, typically of 512. Any text longer than that must be truncated or broken into segments, potentially losing important context. While RNNs could, in principle, process arbitrarily long sequences, transformers forced a different trade-off.